Thanks a lot, everyone, for joining this session. My name is Arif. I'm a developer from Thoughtworks. And here with me is Emily. Hi, Emily.
Hello, I'm Emily. I'm a data scientist also with Thoughtworks.
And so Emily's a data scientist. I'm a software developer, and that is quite a fitting combination, I would say, because what we want to talk about today is how to apply continuous delivery to machine learning applications. Before I get into this, let me say a few quick words about Thoughtworks. So Thoughtworks is an IT consultancy at core. We're quite a bit smaller than, let's say, the big ones. But we are a truly global company, being present in more than 14 countries, 40 offices. You see a couple of the cities that we're present in down there. So I'm calling in from Berlin right now. And I think what makes us stand out is that we believe in the power of diversity. And also we believe that we can actually make the world a better place through what we do. Another thing that we also believe in is open knowledge. And this is one of the reasons why thought workers are quite active in terms of writing books on technology and on agile. So for instance, thought workers have been among the first to write about lean, about microservices, refactorings, and also specifically about continuous delivery. And another publication that we're publishing about 2 times a year is the Thoughtworks Technology Radar. And the Technology Radar is kind of a state of the industry report when it comes to tools, techniques, and technologies in the software area. But what makes the Technology Radar stand out to me is that we only allow ourselves to put topics into the radar that we have actually used in the wild, so to say. So if we find a new framework or a new technology that we really like, but we only played around with it, this is not enough for us to put it on the radar, but instead we want to have used it at clients in real projects so that we can really justify that our experience is solid and that we can include it in the radar. And so one of the techniques that we introduced in the radar in the 2019 edition was continuous delivery for machine learning, short CD4ML. And this is what this talk is mainly about. And we also wrote an article on Martin Fowler's blog on that topic, which goes quite a bit into detail. So if you want to know more, apart from asking us questions, you can also have a look at this article. Now, the topic of applying continuous delivery to machine learning is actually not that new anymore. And for me, all of this started about 5 years ago. And that was actually my first project that I did with Thoughtworks. And that was with Autoscout 24 as the client. And Autoscout, in case you don't know it, is providing, I think, Europe's largest online marketplace for used and new cars. And when we came there, we were meant to build a price estimation application. And back in 2015, this was really quite something new to build this based on machine learning. And so this is how the application looks more or less today. So basically, you can select the make and the model of the car you want to sell, for instance, and then importantly, because you can put a few more details, but then importantly, because it's about used cars, you can say what the mileage is, and then the application will give you a rough estimation of what we think the car is still worth, so that you have an idea for how much money you can put it on the platform. And so this was basically the idea what we were meant to build. And how this looked like in the beginning was that there was this team of developers, and I was one of those developers, and we were meant to build the web application. And then there was this team of data scientists, and they were meant to build the prediction model. And there was a literal wall between us because we were sitting on two different floors. And how this would look like then was that the data scientists, they had already built their first prototype of a prediction model. And then they would pass this prediction model to us, the developer team, and we started integrating this in the web application that we built. And then we would give feedback to the data science team, and then they would change something on the prediction model. And so how this actually felt was that things were pretty slow. So basically, we started integrating the model. We figured out that something wasn't quite as we expected it. We told the data scientist, then we had to wait for the next version. This would just take a day or something. And then the next version of the prediction model would be there. We would integrate this again. Then we figure out something was misunderstood or so. And so that just means that this whole feedback cycle was pretty slow and there was a lot of waiting involved. And then on top of that, and I think this is also the important part, I think there was a lack of empathy in the setup. So basically, the data scientists, they would change ever so slightly a detail on the interface of the prediction model, and that would break the entire web application because we didn't expect it. And on the other hand, the developers would have not much empathy on why certain things are really complicated on the data science side of things. And of course, this probably reminds you of the situation of the separation between developers and operation folks before the whole DevOps culture got traction and was implemented and helped us to really bring people together and create that kind of empathy. So now, us having always been at the forefront of the DevOps movement, we also applied this thinking here. And so one of the first things that we did then after realizing those issues was to bring those two teams together and form pretty much one team, also physically sitting together. So one cross-functional team that would work on this application and the prediction model together. And this was really the most important thing, I would say, and it really was speeding things up a lot. And this whole feedback cycle was much quicker, and we were able to iterate on the product as a whole much better. But so now we were happy applying this DevOps kind of thinking. But then for us, continuous delivery was always one of the most important practices in applying a DevOps culture. And with Thoughtworks, we basically apply continuous delivery. We basically apply continuous delivery on every single project. So that's really perfectly normal for us. And therefore, there we also said, well, we want to apply continuous delivery here as well. You can hear some very young participant. So of course we said let's do this here as well, and this is more or less how this looked like then. We had a prediction model pipeline, and then we had a separate web application pipeline. And in the prediction model pipeline, there's some base data the training is based on, and then you would have the data selection and the model training as a step. And then this yields a trained model. And then usually this trained model needs to be wrapped or transformed in such a way that it can really be served and used in production. And this interoperable model would be put on an S3 bucket in this case. And then on the other hand, you have the web application pipeline, and of course that pulls in the web application source code, compiles, tests, etc., and builds a web application jar, which is then deployed to an AWS EC2 machine in that sense, in that case. And when deploying this to a running web application in production, it would pull in during deployment the newest prediction model from this S3 bucket, for instance. And the idea was to have those two pipelines nicely coupled so that basically whenever a data scientist would make a change, let's say on the data selection or on the training parameters, that this would trigger a retraining of the model, and then this model is automatically published to cloud storage, and then this change in the model would automatically trigger a redeployment of the web application, pulling in the newest prediction model, so that we can make sure that the web application is always presenting the newest high-quality results from the newest prediction model. And also the other way around, whenever we would change something on the web application, it would pull in the newest prediction model when we deploy it. So now this is how we thought of this. And of course, things were not so simply. So we came across quite a few challenges that we kind of didn't expect because we had already applied continuous delivery so often to normal or general software delivery projects before. And also what we didn't anticipate was that it was actually not so easy to convince the data scientists in the beginning of this approach, because they were actually quite happy with working on their machines more locally, training their models locally, and then shipping them to where they were needed. And so some of the challenges that we ran into were, for instance, how to version control the training data. So that's really a basic in that sense here. And then we have issues like that training data and prediction models will not fit into Git so easily because they're too large, and Git is generally built for rather small source code files. And then another issue we had was that retraining a machine learning model in our continuous delivery server would slow down the entire continuous delivery server, because the agents in this continuous delivery server, they were generally sized to compile software and build a little software package, not to perform a machine learning task, which is really makes for quite a different kind of load on the server. And then on top of that, data scientists, they actually wanted to evaluate several solutions at the same time. So technically, when going through with this, they wanted to retrain several models at the same time simultaneously on the delivery server. And then, of course, they also wanted to use analytics notebooks like Jupyter, which are even harder to version control. And then finally, also there was the whole testing topic, like how to unit test data science code that is tied to changing data, and how to prevent behavior changes of the model to break the application. And so those were just a few of the challenges that we ran into when applying or trying to apply continuous delivery to machine learning the first time. And this is where I hand over to Emily for now.
Thanks, Arif. Hi, all. As mentioned before, I'm Emily. I'm a data scientist with Thoughtworks, and Arif brings up a lot of really good points in this anecdote about shipping machine learning in a continuous delivery sense. So actually, can you go to the next slide, Arif? Arif will still be controlling the slide, so unfortunately, don't have full agency here. But when we think about continuous delivery, if we go back to what it was originally created for by when Jez and Dave wrote the continuous delivery book 10 years ago, what they wanted to focus on is that continuous delivery is about change. It's not about a build server or a deployment automation or automated testing, right? Those are all nice and those are all parts of this process, but it's about reacting quickly and in an automated way to changes. And so this quote from the book is great. continuous delivery is the ability to get changes of all types. That includes new features, configuration changes, bug fixes, and experiments into production or into the hands of users safely and quickly and in a sustainable way. And so what this is telling us is that in order for us to achieve a continuous delivery state, we have to be able to understand how our systems are going to change. And to understand how our systems change, we have to understand the ways of working of the people developing our systems. Um, I spoke to Jez and Dave about this. They gave a talk a few months ago on the 10th anniversary of their book, and somebody had asked them what they thought the the trends for continuous delivery would be in the next decade, in the 2020s. And their answer was that they would actually just hope that people start doing continuous delivery for the first time because it's hard. Lots of people are doing things that are um, close to it or approximating it, but to some extent we've confused the idea of tooling with the cultural transformation that continuous delivery really means. And so in order to understand how to do CD for ML, we have to understand how ML systems change. So the next slide, please. Um, so in a machine learning system or any data-driven system, any sort of data-backed application, whether it's a neural network or whether it's something as simple as a logistic regression or even a BI system, you have multiple sources of change. And this could be, this is basically your data, which can change, your models, which are compiled based on data, will also change, and then your actual code for the application itself, much like standard applications, will also be changing. What's important is that these things can change independently of one another. Whereas if you're building, say, a deterministic software solution, such as a backend service or a front-end a micro front-end or a framework, you have one source of change, and that is your code. Here, what we have to do is we have these three independent axes. There's actually four independent axes that I'll get into. And all of those can change, and they can change independently or concurrently. So we'll look at some examples of this. Next slide, please. So code, we understand if we're software engineers. We understand that code changes because we've got bug fixes or we're implementing new features, maybe some dependencies update, or we have to update, a security patch in our operating system that breaks, something that we were doing. We understand this axis of change, right? So continuous delivery, as Arif was describing, has been built around code changing. And so the tools that we have been built to support code changing. So we have GitHub, and GitHub can trigger a GitHub action, which can trigger a build, which can trigger a deployment and run tests, and so on and so forth. This is something that's fairly well understood. And we do have this in data-driven systems as well. So we can't forget about this just for the sake of focusing on the data. We do need to still implement the good software engineering practices. So making sure that things are tested, making sure that we have the right tests in the right place, that we're handling our releases properly, that we're handling our versioning properly, etc. But this is easy, so to speak. Can we go to the next slide? The second axis of change in a data-driven system is our model. So our model could be the compiled artifact that we use to implement some sort of automated decision-making. So for example, a precompiled pickle file that's trained as a random forest classifier to assign, say, incoming support requests into one of four categories to route them to the right customer service agents. So the model here refers to the compiled artifact. So this is, we have code that compiles this artifact, of course. We have scripts that take data, train models, etc. But then we have the actual artifact itself. And this model can change if we have the same training set, but if we partition it differently. If we take a different sampling of our training and test data, the model itself will change, even though our code hasn't changed, even though our data hasn't changed. So this can change by itself. Alternatively, we could have a code change in our training scripts. We could decide, you know what, we don't need a random forest. We can just go with something as simple as a decision tree and implement that. Here again, we have a code and a model change, but without necessarily a data change. But it's important to also remember that our models don't have to be compiled artifacts. Our models could be something as simple as a rules engine that we have encoded in the configuration file. It could be something as simple as implementing a statistical library to do a forecast based on our financial predictions. It could be a Tableau dashboard that we're storing as a SQL model that we're using to predict our payroll for the next month. So models are very broad, and if we are building systems that do intelligent things with data, we have to be able to version these as well. So the next slide. And then we get to data. Data versioning is a hot topic lately. Data is complicated because data breaks down two ways. Um, Next slide. So data we can think of as a function of um, sampling and schema. So in other words, the data itself may change, the distribution can change over time. Your customers get older, you expand into new markets, the world changes. And a schema can also change. This can change because your data model changes and you decide that you're now splitting a field into 4 subtypes instead of 3 subtypes. Or you might be using, say, a third-party tracking framework, and they've decided all of a sudden one day to start shipping a new JSON structure over to you, without telling you, which happens all the time. And so there's ways that your schema can change that can break your model, and there's ways that your data can change, and your data drift can also break your model. And so here, what I like to sometimes say is that data is a snapshot of the universe at a point in time, and a model is a simulation of the universe um, using data, using many snapshots. So it's trying to understand how the universe behaves using a series of snapshots over time. And so we should expect data to change. Next slide, please. So sampling, how does our data sampling change? Basically, we should be prepared for this. Our data is rarely stable. If our data is stable, that probably means that we're not really growing, because if you have the same things coming in and coming out, you're not really able to leverage the power of a data-driven business, because you're not getting new information, you're getting the same information over and over. But sampling will change as customers, create more transactions or create more views. This can lead to all sorts of emergent phenomenon. So if you train a model and your model is trained on data that says that customers will have this sort of behavior, they'll spend this much money on average, and these customers who spend this much money like these things, then as time changes, as your customer base starts spending money in different ways, for example, such as um, uh, the economy changing, inflation could change the overall average value of transactions, or we could have a global pandemic and then people's shopping behavior changes drastically. Um, that is a change in how you're in the fundamental properties of the universe, right? So the shape of your curves will look different. And if your model is trained on a curve that looks like this, and the universe now starts looking like this, then your model is probably not going to be as effective as it could be, and you're going to need to update it. And so what you need to do in a continuous delivery paradigm is be able to detect these changes of the underlying distribution on which you've trained your model, and understand when the domain that your model has been built on is no longer representative of the domain of the universe. So the next slide, please. And then I mentioned schema changes before as well. These happen all the time, and they're usually hard breaks. So can be something like a database schema change where we add or delete a column, but it can also be a change in the type of field. I was on a project once where payment providers changed for the business, and that meant that every transaction code that was um, submitted before a certain date had a certain format, and these values meant a certain thing, and you could map them. And then after a certain date, there were a bunch of different transaction codes. The underlying data model hadn't changed, but those meanings of those codes did, and they didn't map one-to-one with the old codes. And so what we had was this hard break in the data because the schema changed. The meaning of the fields changed. But we can also see things like temporary or sort of invisible schema changes when we use sort of document-based formats, which may not be detectable in our data systems, right? So an example of this is a tracking browser tracking, which may or may not return certain fields in the JSON payload, and it can do this sort of sporadically, and you don't have any sort of you might not be notified by the vendor who provides you third-party tracking, for example. And so what this means is that some of your data has this sort of structure, and some of your data has this other structure. And then it's on your data scientist to figure out what to do with all of that. And this is why, as a data scientist, we often say that 80% of our time is spent just cleaning data, not building models. And so this happens all the time. And we also need to be able to detect changes in our schemas, either that we introduce or that get introduced or imposed upon us. And so all of these things are necessary to track how our systems change. Remember, continuous delivery is about responding to change and getting changes through software into production safely. So the next slide, please. So if we have 4 different version axes, we can expect our systems to drift along them independently or jointly. And so what that means is that we need to build our pipelines able to react in a way that changes can happen either independently and trigger a chain of events, or in parallel and be able to handle those events that happen in parallel together, which makes it a complicated task for actually building software, because we cannot pre-specify the sequential and deterministic order in which our builds should happen. So the pipeline chart, please. Next slide. Yes. Sorry, we're getting to the pipeline slide. So we have, in addition to this, different workflows between developers and data scientists, right? So developer, you have your sort of development trunk, and maybe you're using feature branches or Git flow, or maybe you're making all ThoughtWorkers happy and you're doing trunk-based development. But in either case, what you have is usually in a continuous delivery setup, very short-lived development cycles. So just a few commits, you merge back to master, you push, it goes to production. That's all automated. The next slide. Whereas data scientists have a much different workflow, right? We need to think. We need to lock ourselves in a room for a day or 3 or 2 weeks, or who knows, and build models and train them and do research and do deep dives into the data and clean the data. And it's a very difficult thing, and we need to experiment a lot. We need to try different model structures. We need to try different hyperparameterizations. We need to optimize our hyperparameterizations. We need to try different training data sets. We need to make sure, we need to validate, we need to cross-validate. There's all sorts of things that we need to do. And all of this takes time, and it takes time both in terms of the development energy necessary to do it. So the amount of time it takes me as a data scientist to actually implement the feature. And it also takes time to actually crunch this stuff, right? Training a model still today can take overnight, or even a few days in some cases, depending on your application. So we have different workflows. So data scientists tend to live in a series of multiple parallel spikes, which is a very different type of situation than most developers. And we're trying different things all the time. So the next slide, please. So this is, here's where we have our pipeline. So because of this, right, and partly because of the siloed model that Arif mentioned earlier, is that we have different types of pipelines building our system. So we have the data pipelines, right? So this is what our data engineers build, right? They take in data from our production systems, and then they take it from one place, they put it into another place. Maybe they feed it into a data lake or a Kafka queue. And maybe they're putting it into an OLAP cube, or taking it out of an OLAP cube and putting it in a data lake, or whatever it is that they're doing. So these pipelines will change. When they change, our ability to update our machine learning systems change. Then we have our machine learning pipelines, which is our training, validation, etc. How we actually go from data to model. So you can see that data comes in the pipeline, comes out the pipeline. We add some code into the machine learning pipeline to mix with the data, and out of that comes a model. And then we have a deployment pipeline where we have to have our devs put together some code to wrap around this model and then to ship it out to the cloud. And then hopefully we have working software at the end. This is a lot of pipelines, and I really wish that we could invent some words that weren't pipeline to describe this, because everything is a pipeline and you never know what people are talking about. Because on top of this, you also have your continuous delivery or your build pipelines that orchestrate all of these things. So you have a pipeline of pipelines, and that's not even counting your hiring pipeline. So what we need to do is figure out ways in which we can limit changes to the right pipelines and to trigger these changes in an automated way that makes sense. So if our data pipelines change, we need to be able to understand whether or not that change is going to require us to trigger a machine learning build. And if that machine learning build is going to require us to re-trigger a software build in those deployments, or if we can just go straight through to ship the new artifact and plug it in without having to do a software update. The next slide, please. So if we put all of this together, I'll walk through this fairly quickly. The data science continuous delivery workflow will look something like this. We begin with discoverable and accessible data, which is the most important part. Make your data scientists happy, give them lots of good data that is clean, and then allow them to build their models. So we start with that. We write some code to train it, and we start with a set of parameters with which to train the model. Then we evaluate it. We use some test data to see how that model is doing, obviously. And then we sort of productionize it. And this is the step where lots of people sort of stumble and fall, because it's a very simple thing to say, yes, just productionize my model. But it's actually quite difficult, and there's a lot of tooling that's been built up around this specific step. So TensorFlow serving, there's some other things out there that are designed to make that easier. But that's still not a continuous delivery solution, right? Because we still need to integrate our testing. We need to make sure once we build and integrate it into our systems that the model actually performs the way that it's expected to. One of the sort of quirks of machine learning is that we, as data scientists, we spend all of this time cleaning this data and making it nice and getting it into a place where we can do something with it. And then we train a model on it. Well, the data is messy because the world is messy. And then so we clean all this data and build a model around this clean data. And then we ship it off to a world where the data is messy again. And then we expect it to perform properly. So we need that integration testing. And then we need to ship it in an automated way. To deploy it. And then finally, we need to have that monitoring. So we need to be able to assess in real time how our model is doing in production systems. And we actually need to generate production data, because what we want to do is now close the loop, the last slide here, to close the loop to generate new discoverable and accessible data, because our model that was trained on nice pristine data is now in a world of messy messy data, and we need to be able to identify issues with it early on. So that's all I have for that, and I'll hand it back over to Arif for now.
Thanks a lot, Emily. So now going back a little bit from this conceptual view back to kind of what tools and technologies do we need to make this happen. And so quite generally, this is pretty much what Emily just iterated over. We first need a way to have discoverable and accessible data. That's really the foundation, right? Then we need tools and technologies for version control and artifact repositories. We need a continuous delivery orchestration solution to combine those pipelines. And it's usually, because we have so many pipelines and they need to be orchestrated, it's usually not enough to have a just a continuous integration solution, but actually one that really supports continuous delivery. And then, of course, we need an infrastructure to actually run all those experiments and applications. And we need a way to assess the performance of a model. And finally, we need to be able to monitor and observe the behavior of the model and our products in production when they're being used. And so now I want to present one exemplary tech stack that we have used to build something like this. But overall, here at Thoughtworks, we're really not tied to specific technologies or solutions. So we usually use the tool, which is pretty often an open source tool, which happens to be the best fit for the problem at hand. So this is really just one example of a stack how we implemented this. So for the data accessibility, in this case here we used Google Cloud Storage. For the version control, of course, we used Git, but we use that in combination with a little tool called DVC, and DVC means data science version control. So this is a little command line tool that helps to bring kind of the data science workflow that Emily talked about earlier to Git version control and support it a little bit better. And then for continuous delivery, in this case, we use GoCD. GoCD is a continuous delivery tool built by Thoughtworks, and it's still being built and improved by Thoughtworks. But we also use many other continuous delivery tools such as Circle CI, Concourse, etc. But we still feel that GoCD is a good tool for those kind of problems. Then in this case, for the infrastructure, we use Google Cloud Compute and Docker, of course. Then for the model performance assessment, interestingly, there are not so many tools around that we're aware of that are really built for model performance assessment. And one of those tools is MLflow. MLflow actually does also a lot of other things, but we found it to be one of the few tools for model performance assessment. That is why we use it here. And then for monitoring and observability, we apply a normal EFK stack, so Elasticsearch, Fluentd, and Kibana, as we would do with pretty much every other software project. And so now, because this is still a developer conference, I want to give a little demo of how this actually looks and I want to focus primarily on those three pieces here, on the version control, on the continuous delivery orchestration, and on the deployment, basically. So what I want to go now in very quickly is I want to show you a setup of pipelines in GoCD. So that's what you see here on the left. I want to see the application, an example of the application that is being deployed. And I just generally want to show you the workflow of a change, especially a change about the model training being pushed, then being tested and evaluated, and then, if everything goes fine, being deployed. And keep in mind those two delivery or those two continuous delivery pipelines that I showed earlier, the prediction model pipeline and the web application pipeline that are coupled, because this is exactly what you're going to see now. So going to the other browser tab here, you can see now this is the dashboard of a GoCD continuous delivery server setup. And you see here two pipelines, and they're in one pipeline group. And you see on the left side here, that is the pipeline that builds the web application. And this is the pipeline that trains and builds and evaluates the machine learning model. And when you check this value stream map view here, then you can also see how those two pipelines are connected. So both pipelines pull from Git the changes, but then you see that the machine learning pipeline creates the model, which is then consumed by the web application pipeline. So the web application pipeline depends both on changes from Git, but also on artifacts that are being produced by the machine learning pipeline. And so I want to demonstrate this a little bit. So those pipelines that you see there, they are connected to my fork of the CD4ML workshop repository. By the way, you can go here to the CD4ML workshop repository in the main Thoughtworks GitHub organization. It's a repository that walks you through many of the concepts, and you can try a couple of things out. And it's all freely available. So now I'm looking here at some of the source code for the model training. And keep in mind, this is an extremely simplified example. So here we apply a decision tree approach to a sales forecast. And basically, I'm doing now is that I'm going to just edit this in place here. And I change the approach down here from a random forest to a decision tree. And so that has been committed and pushed here now. And now what we see here in a second is that this will trigger the machine learning pipeline to rebuild and retrain the model because something has changed. Quickly, that you also get an idea what this is kind of building. This is the application that is being built from this. As said, it's a very simple example application. It's about a sales forecast. So basically, the idea is that you can say in a grocery store, day after tomorrow, how much milk is going to be sold. And then it's going to say 6 here, or let's see, also 6. Oh, well. Now let's get back here. So this is what I just showed is the application that is being built and deployed by this pipeline, this application pipeline here on the left, right? And on the right, you now see that because of my little change that I did to the
Unmute.
I'm hearing someone.
No.
So
People around us.
someone is not muted who thinks he is muted, I think. So we see now this has been triggered here because of the changes in the data science code, so to say. And we see what's happening here. We can actually go into this train, evaluate, and publish step. And we see that this is actually calling this little tool that I mentioned before, DVC. And it says DVC repro, which means actually to reproduce a model. And we could see that it was going here through loading the input data, splitting the data into training and validation data, and then basically using this decision tree regressor to build a model. And now, interestingly, it failed. So you see here that we actually have a failing build. And it failed because the accuracy was not good enough. So we expected basically the error to be below 0.8, and that was not the case. And so that's why it failed. And when we talk about continuous delivery, then a failed build is a really great thing because it prevented us from shipping something of suboptimal quality to production and to the user. And that's exactly what we want. We have those quality gates here that make sure that this is not being pushed to production. And now what you see that is not happening is that this application pipeline is not being re-triggered. So basically they are connected, but because this failed, the application pipeline is not rerun, and the application that is being deployed here is not changing because it didn't get a new prediction model that was good enough, so to say. And so then let's quickly change that back here. And let's use a random forest here again, which is just kind of creates a bit more accuracy, and that should be enough to bring us across the threshold. So let's get back here, and then we should see this fairly quickly. And then we can also see that kind of here in this web application pipeline, we see that there's a build and publish step, and then it's deployed afterwards. So let's wait this second for this to be run. Actually, I'm a bit impatient, so I will just trigger this here manually. You saw it before that it is triggered within, let's say, 30 seconds by the push to Git. And now we can check again what is happening here. So this is now waiting for an agent from the GoCD server to be assigned to this task, which is then doing the retraining. And now we want this to go across the threshold that we expect to be republished.
So while we're, I'm sorry,
go ahead.
good. I was going to say, while we're waiting on the build here, one of the things, one of the principles behind continuous delivery, of course, is continuous improvement. And so one thing that you could do, I'm not saying it's the best idea to do it, but you could do something like this, is every time you have a model that gets built, you have a new score. And ideally, that should be your best score. And you can configure your pipeline to always fail builds that do not beat your latest top score, so that you can actually build a pipeline that pushes you towards continuous improvement. Here we have a simple fixed threshold, but there's all sorts of things that you could try to implement that would keep your pipeline, your continuous delivery pipeline, that is, evolving, so that the product that you build is continuously better, and it can enforce those quality checks on you at build time.
Yeah. So as mentioned, kind of this this very simple threshold is really the easiest and most simplified example of a quality gate here. In reality, obviously, we have much more complicated quality gates and also different quality gates. So now we see that this actually passed because the quality of the trained model was good enough. And now we see that because this passed, now this re-triggered the building and redeployment of the application, of the web application, which is now going to pull in the prediction model, which was pushed to a cloud storage by this pipeline. It's being consumed, and then we see basically when this stage here goes first yellow and then green again, then we'll have a redeployed application consuming the newly retrained and redeployed prediction model. And I think that's pretty much it for that little demo that I wanted to go into. And with this, I will quickly step back into the presentation and hand it quickly back to Emily to wrap things up.
Sure thing. Thank you. So what you could see there in that demo is that there's a few things that are happening. Once we could see how the machine learning model change triggered a pipeline rebuild. What we would also see is that if we change something in the code that was not a machine learning change, if it was, say, a change to the front end, it would not trigger the retraining part of that pipeline. So our pipeline was smart enough to detect the context of changes. And that's an important feature in any continuous delivery build tool, is that you want it to be flexible enough that you can configure it to be smart enough to only do the things that it needs to do. And not every build tool has that functionality, and it can be a real hindrance. The other thing to point out in that is that all of our code was living in the same repository. So we were going to more of a self-contained model where the application lives all together. We don't have to do it like that. You can have multiple repositories, but having a mono repo is one way to build an app, and you can have a mono repo, and it doesn't necessarily also have to be a monolith. You can have a mono repo microservice with multiple components. So when you have this continuous intelligence, if you want to achieve this continuous intelligence state, right? So when we tie all of this together, we have to think of the bigger business context. So we start with acquiring data, and we want to, pull these in from our production systems. Maybe we're purchasing data, maybe we're using third-party trackers, etc. Then we take this and we need to store it. We need to archive it. We need to clean it, curate it, featureize it. We need to understand what are the features, what are the anomalies, what are the edge cases, why are there edge cases? Are we documenting the situations that led to data being messy in some time frame, etc. From that, we can then build a model by training and predicting using our machine learning techniques that are now actually fairly commoditized. You don't even need to have a ton of experience in designing actual machine learning algorithms to implement machine learning models these days, because the frameworks are so easy to use and training is so present. Once you do that, the hard part then again, of course, is productionizing it. One challenge here that we don't often talk about is that data scientists work in one stack. That is often very different than the stack that our backend systems use. So you very rarely see data scientists slinging Python or Java code, for example. They're usually writing in Python or R. And then we have to integrate this code, this artifact that they built in a different language, in a different framework, different stack, into our systems. And there's many ways to do that, and you have to pick the right one for you and for your organization. And then you ship this out into the real world. And what we want to see is not that this is a one-time fire and forget. What we want to see is that this creates a closed loop feedback system that leads to more data, that leads to changes, right? So the ideal situation is that the models that we implement actually change the way that our business behaves. And because it's changing the way that our business behaves, it needs to be updated over and over and over. We don't just want a model to do the same thing, but maybe more efficiently. I mean, that's one benefit. But it's even better if we can use the model to understand, to identify sales that should happen, or to identify traffic that should be rerouted. And that will change the way that our business operates. And so ultimately, with that lesson, sort of close with the one tagline that I always like to bring out when talking about data science, is that the objective functions that we use should be linked to business value. There's lots of research, fantastic, amazing research being done in machine learning right now. That research often is built around accuracy metrics and objective functions and cost functions, et cetera, that don't have any value, right? There's no actual value from an R-square score. There's no actual value from a sensitivity and specificity ranking for a model. There's only business value if you can prove that those things, that an improvement in those things actually brings you more money, more customers, more stock, flying out your doors, more traffic coming into your website, whatever it is. So that's the core thing. And it's not just doing data science for doing data science, it's actually doing data science for business. And that if we can focus on that, then we can identify the cultural challenges needed to get to a continuous delivery state. That's all that I have. And thank you very much.
Thank you so much.
I think we have 5 minutes for some questions, which can be asked in Slack, I believe, or probably just through the conference.
Yes, indeed. So everyone can just, I think, unmute themselves if they want to ask a question. Otherwise, I can maybe check here.
Showing the secrets of the speakers lounge, Arif.
Yes, very much. All right, I do not see any direct ask at us.
We are conference room 3. I see a slide here. Great talk. Thanks both. Are the slides going to be available? Would love to share with my colleagues. I believe the answer to that is yes. We can make the slides available in some way, shape, or form if they're not already being made available through the conference website.
Yes, I think also I think an older version of the slides is also available in the in this repository here, even that I mentioned before, the CD4ML workshop repository. But we'll definitely make them available. Any other questions in the room?
Jacob also mentions that the talk will be recorded and will be available on YouTube. All right. So I will also, just as a little bit of a pitch, this afternoon be discussing this context in more of a case study fashion, where I'll be talking about patterns and pains of developing data-driven systems in a continuous delivery context. So basically, lots of observations on what businesses are doing right and what some of the common pitfalls and things that lots of businesses do wrong in shipping data science products, data-driven products out the door. So I believe that is at 4 p.m., if I'm not mistaken. So
I think so.
Hopefully we'll see you there.
Fantastic. Then thanks again, everyone. Thanks for coming to this session. And I wish you a fantastic rest of NDC Portal.